Good morning, everyone. I'm Greg Weatherby with the U.S. Geological Survey, the conference chair, and thank you all so much for being here in the last speaking session. We also have the poster session later on after this session, and which will go on. I think we have that scheduled for a couple hours, 3 hours maybe. It's going to be a different experience as poster sessions go. This morning. We have Dr. Pamela Templer from Boston University, who will chair the session on atmospheric deposition in a changing society. And very glad to have Pam with us this morning and all the speakers. And thank you so much for all of your participation. Remember to keep on mute if you're not speaking. And when you're done with your presentation, please stop sharing your presentation. And other than that, I think that we're pretty good for logistics. So Pam, I'm going to hand it over to you.
Great. Thank you so much, Greg. And thanks to all of the NADP staff for putting on just a wonderful meeting as usual. Good morning, everyone. As Greg said, this is session 8, Atmospheric Deposition and a Changing Society. And I'm excited to introduce our first speaker, Luis Miguel Urbina Leonor. And he is going to speak with us about effective atmospheric deposition on built heritage. Go ahead, Luis.
Okay. First of all, thank you for hosting us. And I'm Luis Miguel Urbina Leonor, and I will talk about the effect of atmospheric deposition on built heritage in Mexico. This work was done working with Drs. Rodolfo Sosa, Rogelio Soto, Gilberto Fuentes, chemist Ana Alarcón, and biologist Pablo Sanchez at the Center of Atmospheric Sciences of the National Autonomous University of Mexico, or UNAM. But first, a word on cultural heritage. It refers to the several different expressions developed by a community that represent their way to understand the world and the different lifestyles it leads to. Cultural heritage can be tangible or intangible. The first one has materiality as artifacts, building remains, or art. The second one refers to cultural assets that represent something that cannot be taken, even though they might have a physical representation, as traditions, rituals, customs, or even food. Each kind of heritage faces different problems concerning its preservation, but among the threats tangible heritage is exposed to, environment seems the main one. Although the everlasting preservation of a property is virtually impossible, knowing the main decay mechanism and the factors controlling it is important because we can develop materials and strategies to slow down the damage, especially for movable objects. Built heritage refers to monuments, building, or building groups. Mexico hosts a large amount of built heritage classified by its chronology as pre-Hispanic, that's before 1521, historical between 1521 and 1900, and artistic from 1900 onward. Besides the 27 cultural and 2 mixed properties listed by UNESCO, there are 42,614 archaeological sites, 18,770 historical monument areas, and 121,531 artistic monuments of national interest, most of them located in the map, for a total of 182,915. That's a huge amount. In the image, you can see the Ruperstrian paintings in one of the 7 caves in Baja California Sur, Paquima in Chihuahua, the San Francisco Mission in Durango, belonging to the Camino Real de Tierra Adentro, and Luis Barragan's house, all of them declared UNESCO heritage sites. Work for its preservation is important, but nowadays it is a hard task, for little is known on the effect environmental conditions have in materials other than limestone or marble. Environmental factors affect in different ways. The effect of pollution on built heritage did not begin with industrial revolution. There are several sources mentioning them since ancient Rome. Traditionally, wet deposition was considered the main decay mechanism. That is because as rain droplets fall, react with contaminants as carbon dioxide, sulfur dioxide, and nitrogen dioxide, forming carbonic, sulfuric, and nitric acid respectively. Since most work done on built heritage is for carbonate stones, this acid reacts with calcite or dolomite, dissolving them. And that's the reaction shown in the slide. That can produce loss on surface that, although not much numerically, might represent an invaluable loss when it comes to aesthetical or when they're used as aesthetical or historical sources. And that's an example of a Mayan stela, where the slightest loss may represent the difference between understanding or not the depicted epigram. This stela represented is not legible in its totality, probably because of the material loss caused by environmental factors and incorrect intervention with cement visible at the bottom here. Nowadays, it is known that most mass loss of carbonaceous stones is due to dry deposition. It can happen through several mechanisms, as the one presented here, Uh, that can be electrostatic capture, Brownian deposition, thermophoresis, Stefan flux, inertial impact, gravitational deposition, all of them depending on the surface, particle size, and thermodynamics. By means of dry deposition, both particles and gases can interact with surface, and as an example, sulfate dioxide, it's absorbed to the surface of carbonate stone, reacts with the substrate to form sulfite, which quickly transforms to gypsum. This is considered the main decay mechanism because after the formation of gypsum, since it is much more soluble than calcite, the difference is around 2 orders of magnitude, and is less coherent, it's easier the detachment and lixiviation of the damaged crust because of rain. However, this transformation is not completely undesirable. A study in 2006 showed that a certain amount of soiling is not only tolerable, but also desirable in several cities in Europe. So they can have like an ancient look. And that provoked that scientists in Europe start to develop damage function as the one presented here, which considering different variables like ions concentration in water position, the volume of rain, concentration in the air of different compounds, temperature, or even days with relative humidity above 60%, to know the amount of mass loss, often called surface recession because marble is a so low porous material that its behavior is almost like a metal. Among the damage function, it was shown in 2002 that the Lipfer function, the first one presented here, is the one which with the best performance compared to the others, compared to real conditions. Knowing that some future climate scenarios were done, consider how much limestone will corrode presented in the slide. Above, you can see the conditions estimated by a model in 1960, and under it, you can see that forecast using the same model considering climate change for 2100. However, when working with cultural heritage, the you can see the difference mostly in the Scandinavian peninsula. However, when working with cultural heritage, it's important to remember that not all the damage will be due to chemistry. There are some other mechanisms, cell crystallization, thermoclastism, cryoclastism, or biodeterioration. All of them considered in different researches. Thermoclastism is the damage of the material because of the expansion contraction cycles, and cryoclastism is the damage of the material because of the freeze thaw cycles. However, as I said before, damage function were engineered for European conditions because most studies have been done in Europe, but conditions in Mexican geography are different in general because it's located mostly in tropical latitudes instead of medium latitudes, resulting in not having the same number of seasons. Instead of 4 seasons here, there are 2. And the insolation it receives, it's much higher, and even building materials used change. And for the building material, the main difference is that although there were some volcanic stones used in southern Italy, the main building material used was carbonate stones. That means marble, limestone, or dolomite. Hence, damage function can be used as indicators, but not only in Mexico, but in most Latin American countries, we need to start a slightly different approach towards heritage, considering all that it's known, but knowing that the conditions are not exactly the same. And to do that, we need to deepen our knowledge on building materials, performing different tests and evaluating the different variables that might affect them that are often overlooked in Europe as thermoclastism, and ignore some of them that do not represent a problem as cryoclastism. In situ exposures are essential, but are also very time consuming, and environmental monitoring data is not always available. So a powerful tool that we must use to provide at least a glance on the effect of different environmental variables is accelerated weathering. It is the simulation of medium to long-term effect of some parameters in a material. Those kind of tests are common to evaluate coatings on metals, like the one presented here to the left. But the group I'm working with developed an accelerated weathering chamber to wet deposition where a solution with virtually the same chemical composition sampled on site was irrigated above undamaged samples of stone. The reason for the 2 containers was to keep the hydrostatic pressure constant, and so the irrigation was constant too. The rain volume along with sample area and the irrigation rate was used as a comparison to real-time exposure. And an example of calculation here is presented for El Tajín conditions, when 1,200 millimeters of rain irrigated in an area of 25 square centimeters at a rate of 1 milliliter per second. It tells us that it will take 50 minutes to simulate the volume of rain that will fall in 1 year. Using the wet deposition data collected from August 2002 to April 2003, the worst case scenario was used to simulate the conditions building materials was exposed to for El Tajín. The building material is a limestone with a porosity of around 11%, and using a solution with the composition of the lowest pH range sample collected at El Tajín that you can see in the slide, very rich with chloride and sodium because it's near the coast. And samples from a local stone that was not part of any building were irrigated with a volume sample that it will get in 23 years at 26 Celsius degrees and a relative humidity of 80%. The results are shown in the table to the right, to an average mass loss of about 22 milligrams per year. Here, it was supposed that only calcite will dissolve, although the material presents some quartz and feldspar that can also dissolve, mostly with calcium, and gypsum was found as a corrosion product which tells us that there are some dry deposition. A similar experiment carried out on masonry mortar was done. Since it is a more porous material and the water absorption is higher due to the presence of several hygroscopic minerals, mass loss is much higher, around twice the mass loss of limestone. You can see it right. And it was performed to know the worst damage cement construction could have in South Mexico City. The saline solution to perform the accelerated weathering test was selected after the mean sample rate composition from the most acidic rain station in Mexico City presented in the table. Oh, I forgot to mention that these stations for wet deposition follow the NADP recommendations. The higher amount of mass loss is because as porosity increases, more water can penetrate and dissolve the material, and also wash out some minerals. Some other researches were done outside the group. I will not talk about them. It's important to remember that they exist and they were done in the southeast area. So that's Campeche, Yucatan, Tabasco, and Veracruz, which made us realize the importance of performing new tests, not only to update the data already obtained, but also begin to work with different decay mechanisms as salt crystallization and dry deposition. So 3 sites belonging to the 3 temporalities in Mexico's history, built with different materials. The Templo Mayor, built among other materials with the Santle in downtown Mexico City. The San Juan de Ulua, located in Veracruz, built with a coral limestone called mucar. And Ciudad Universitaria, the main campus of the of the UNAM, built mainly with Portland cement and masonry mortar in South Mexico City. Besides the characterization of the material and exposure in situ, we will perform different accelerated weathering tests. Wet deposition, as mentioned before, dry deposition in another chamber where conditions as temperature, relative humidity, or pollutants concentration can be controlled, and how prone they are to salt crystallization, exposing them to saline solutions with chemical compositions similar to rainfall. As an example of the conditions, I'll talk about Ciudad Universitaria, the main UNAM campus, and it is a UNESCO Cultural Heritage Site declared because it constitutes a unique example of 20th century modernism, exhibiting the integration of urbanism, architecture, engineering, landscape design, and fine arts, combined with references to local traditions. And there is available information of automatic monitoring stations of temperature, relative humidity, wind speed, wind direction, accumulated rain, rain events, the number of events, irradiation, sulfur dioxide and nitrogen dioxide concentrations. And the station is located here, and this is the main campus. It's around 800 meters apart. And here's a picture. And I would love to present some results, although because of the pandemic, we were not able to start the experimentation. But summarizing, although the research is done at an excellent starting point, we need to start exploring different approaches. Carbonaceous stone materials are important, but we need to remember that they are not only building materials, because different natural stones have been used worldwide. They are not the only materials. And finally, there are some numerous different decay mechanisms, not all of them chemical, but all of them related with the environment. So we need a transdisciplinary approach towards the preservation of built heritage for future generations. Thank you very much.
Wonderful. Thank you, Luis. Do we have any questions? Feel free to raise your hand in the participant window or to say in the chat that you have a question. While we're waiting, I'll ask you a question. Really interesting study. I really enjoyed it. I'm curious, do you think you can apply any of your results to areas of the world that have karst topography, so areas that are dominated by calcium carbonate naturally?
Yeah, that's our goal, like long-term goal, to be able to use satellite data to forecast the decay different materials will have in different parts of the world. But the problem to do that here is that we do not have the conditions that apply here. I don't know if I'm being clear. So our goal is to make like an atlas of the conditions that will provoke decay and which is the main mechanism controlling it. So we can start different strategies to, I don't know, to lower it.
Sure. Thank you. We have a question from Mike Bell.
Hey, Luis. I'm Mike. I work for the National Park Service, and most of my work is looking at figuring out the level of pollution that causes changes in ecosystems. Do you think you can figure out like a threshold of concentration through this process, as this is too much or this causes too much weathering?
Yeah, we want to do that. It has been done in Europe. There's a threshold for different contaminants and even for black carbon, but I will not risk saying that now, but I think we will be able to do that. To say,
that's
like,
great. I look forward to seeing those
acceptable decay, let's say.
Perfect, thanks.
Wonderful. Shin O'Hara has a question. Different damage functions have different input environmental factors. In Mexico, what environmental my chat moved. In Mexico, what environmental factors are essential for assessing national corrosivity or corrosion map in ISO 9223? Damage function for metals, temperature, and relative humidity, sulfur dioxide and chloride too.
Well, now I think we haven't finished the research yet, but I think it will be the concentration of sulfate and nitrate in wet deposition. I think it will be one of the most important. And I think it might be also the irradiation, because since there's so much irradiation here, the contraction expansion cycles can be really important. I guess they are, but we cannot ignore some others, like concentration of air pollutants like sulfur dioxide and nitrogen dioxide.
Wonderful. So in the chat, you're getting many congratulations on a great presentation. Greg Weatherby asks, what is the outlook for historic site degradation with respect to trends in acid deposition in Mexico? Is acid deposition creating more weathering or less?
Well, the problem here is that I think they synergize, because also in general, dry deposition is it's guilty for most decay. If wet deposition doesn't arrive, so it can wash out, it will not have a visible effect. Yeah, aesthetically, yes, but not like in mass loss. So I will not say any of them, but both of them.
Wonderful. We have more accolades in the chat. Are there any other questions? We have a few more minutes left. Well, I'm very pleased to introduce Jenna Rindy, a PhD student in our group, and she's going to talk to you about the effects of urbanization and fragmentation on atmospheric nitrogen deposition, nitrogen oxides, and ozone in New England forests. Take it away, Jenna.
Okay. Is everyone able to hear me and see my slides? All right, great. Thank you so much, Pam. I'm excited to present to everyone our new results on nitrogen deposition and nitrogen oxide and ozone concentrations here in Boston. Let's start here with, why are we interested in examining specifically urban areas? We know that more than 50% of the human population now lives in urban centers, which greatly affects atmospheric inputs of nitrogen because of increased anthropogenic activities like vehicular emissions. So much so that a meta-analysis from our lab found that nitrogen deposition is approximately twice as high in urban areas than rural areas globally. We do lack studies on how increased nitrogen deposition impacts the biogeochemical cycles in urban areas, but we're beginning to change that by sampling in urban areas. Specifically, the photo on the right here was taken at Boston University, which is in an urban center and houses our urban forest. The photo was taken on top of the building that is home to one of the few urban NADP sites in the US. Why is it important to include nitrogen oxides, which I'll refer to as NOx moving forward, and ozone in our urban forest studies? Urban areas make up approximately 2% of the global land area, but they produce the majority of our NOx emissions. The increased NOx emissions in urban areas can contribute to higher formation of nitric acid, producing more acid deposition. Additionally, increased nitric oxide brings more reactions with free radicals in the atmosphere to form ozone, which we know is a greenhouse gas. While studies show acid deposition is detrimental to the health of soils, we find that not only does ozone decrease pulmonary function in humans, but also damages leaf chlorophyll, in turn decreasing carbon sequestration in plants. And to the right here, you can see an example of what ozone damage looks like on a vegetable leaf plant. In addition to urbanization, we're also including fragmentation or edge effects in our study. Forest fragmentation occurs when an area of forest is removed to make room for built components such as infrastructure or power lines. You can see here an example on the right, in which a forest is cut to make way for a road. Globally, approximately 20% of remaining forests are within 100 meters of an edge, just like this photo. Studies found that up to 56% more pollutants and nutrients are deposited at forest edges compared to forest interiors due to increased exposure of trees at the forest edge to pollutants. To the right here, you can see an example of one of our study sites that is exposed to a road at its edge. Finally, studies specifically in the area of our study show higher nitrogen deposition in throughfall under canopy than in bulk rainfall. Overall, we're interested in working to understand if forests are experiencing greater exposure to nitrogen deposition and atmospheric pollutants due to the combination of urbanization and edge effects. It's also possible that there are seasonal differences in these measurements that we have not yet accounted for. We know that one of the most effective ways to study canopy processes and deposition of nutrients is through the field method of throughfall compared to bulk deposition. Additionally, we know that due to the damage Nox and ozone cause for both human and vegetation health, the ambient concentrations of each of those pollutants require further investigation in terms of urbanization and edge effects, and we can investigate those through the use of passive sampling. With background information in mind, we developed a study question. Are edge effects more prominent with increased urbanization? We first hypothesized that urban forest edges will experience greater throughfall nitrogen deposition compared to forest interiors. Based on past studies, we expect to see higher nitrogen in throughfall than in bulk deposition, and we also expect that urban forests will experience increased throughfall nitrogen deposition compared to rural forests. Second, we hypothesized that urban forest edges will experience greater Nox and ozone concentrations compared to forest interiors. We expect to see high summer ozone concentrations due to increased sunlight, and we expect that urban forests will display higher Nox and ozone concentrations than rural forests. To answer our research questions, we developed the Urban New England project. We chose our study area indicated here and by the white star on the map because New England is the most populated area of the US per land area. New England also has 83% of its land covered by forests. This amount of forest cover means that the area also has many examples of forest fragmentation and urbanization for us to study. My study is part of a larger study examining the drivers of carbon sequestration in forests, in which we established 8 sites across an urbanization gradient, which you can see mapped here. Our sites extend from Harvard Forest, which is located in central Massachusetts, to the center of Boston. In terms of the sampling layout for all 8 sites, we developed a transect from the edge of each forest at 290 meters into the interior, in which the edges are either up against a road or up against a field. Measurements for this particular study were taken at 0 meters and 90 meters, but we also conducted other measurements such as soil respiration at these other distances along the transect. The gray circles here represent our through-fall sampling locations, and the black circles represent the Nox and ozone sampling locations. We had 3 replicates of through-fall resin columns at both 0 and 90 meters, as well as 3 replicates for bulk deposition in an open field corresponding to each forested site away from canopy cover. Additionally, we had 2 replicates of Nox and ozone passive samplers at both 0 meters and 90 meters into the interior at each site. In terms of sampling period and analyses, our through-fall and bulk collectors contained ion exchange resin, which leaches ions from precipitation as it passes through the column. We had 2 sample periods in 2018, which represented the middle to late growing season. In 2019, we had 5 sample periods, which represented the entire growing season, and all columns were deployed in approximately 5-week periods. Through-fall samples were extracted and analyzed for ammonium, nitrate, and dissolved inorganic nitrogen using the microplate colorimetric method. Our Ogawa Nox and ozone passive samplers contained pads inside of them, which reacted to the gases as they passed through. We had 3 sample periods in 2018 from the middle to late growing season and 5 sample periods in 2019, which represented the entire growing season. All passive samplers were deployed in approximately 3-week periods. The pads were removed from the passive samplers, extracted, and then analyzed using high-performance liquid chromatography for Nox and ozone. So what did we find? I'll first show through-fall results, and then I'll show passive sampler results. You will see a similar layout for most of the plots, so I'd like to let you know what you'll be looking for. In general, you'll see 2018 data on the left and 2019 data on the right. Additionally, you'll see ammonium values on the top 2 plots and nitrate values in the middle 2 plots. The sum of the ammonium and nitrate values will be displayed in the bottom 2 plots as total dissolved inorganic nitrogen. The passive sampler plots will follow a similar layout. Here you're seeing each of our through-fall nitrogen values in kilograms per hectare per day on the y-axis. On the x-axis is installation period, or the range of dates that the samplers were deployed in the field. The values are split by distance from edge, with black being edge values and gray being interior values. The first thing we're able to confirm using these plots, shown in the blue rectangles here, is that the values are within the same ranges across both years. Additionally, you can see that the patterns here are driven mainly by ammonium, as our ammonium values reach approximately 0.015 kilograms per hectare per day, while our nitrate values only reach approximately 0.005 kilograms per hectare per day. Finally, you can see here that we have evidence of enhanced deposition of nitrogen in the spring, which decreases over the rest of the growing season. This could be attributed to canopy processes such as microbial activity. Now I'd like to show bulk deposition compared to through-fall deposition in a full growing season, so I'm only showing 2019. The bulk deposition here is shown in black, and the through-fall deposition is shown in gray, with the y-axis here being total dissolved inorganic nitrogen in kilograms per hectare per year. The x-axis here is an arrangement of our sites, which is by percent ISA. And percent ISA is an urbanization metric indicating the amount of impervious surface area. So the sites go from most rural on the left to most urban on the right. The highest bulk point here in our rural area corresponds to all 3 rural sites located in central Massachusetts at Harvard Forest. We did check over this value multiple times, but continued to find that the bulk nitrogen deposition was significantly higher at the rural site than at the urban site. This is interesting because we generally find throughfall values to be higher than bulk. It is possible that this can be attributed to fertilizer input. The county in which Harvard Forest is located has the most farms out of any Massachusetts county at 1,500. And for reference, the next county with the most farms has 800. Additionally, our sampling county has the largest acreage of farmland. Here, I'm again showing 2018 on the left and 2019 on the right. The y-axis is throughfall, ammonium nitrate, and then total DIN from top to bottom, this time with percent ISA on the x-axis. So each individual axis goes from rural on the left to urban on the right. The values are split by distance from edge, with black being edge values and gray being interior values. We did investigate using two different urbanization metrics, the other being distance from Boston, but we found that while percent ISA showed significance, distance from Boston did not. This could be attributed to suburban contributions. In general, we found that urban forest edges do show significant nitrate deposition. The arrows here show you where you can find the most urban sites at the forest edges. We believe that this significance is due to the contribution of fossil fuel combustion in urban areas because it aligns with a previous study from Steve DeCina that reveals a positive relationship between vehicle traffic in Boston and local nitrogen deposition. Moving on to our Nox and ozone results. We find that ozone concentrations decrease throughout the growing season. On the left side of the plot are 2018 data, and on the right side again are 2019 data. The average NOx concentrations are on the top half of the plot, and the average ozone concentrations are on the bottom half of the plot in parts per billion. All values are split by distance from edge, with black being edge and forest being gray being forest interior. These plots are over time, with installation period on the x-axis here. In NOx, we see elevated spring concentrations in 2019, indicated by the blue arrow, while these spring values are quite similar to the summer and fall values found in 2018. However, we do see elevated spring concentrations in the first installation period for ozone in 2019, with a decrease over the rest of the growing season. Massachusetts Department of Environmental Protection has ambient ozone sensors placed across the state. When looking at those values, we see that ozone is actually highest in the midsummer. So this is interesting because it implies higher forest concentrations than ambient concentrations. This plot is again showing 2018 values on the left and 2019 values on the right. We have percent ISA on the x-axis, which again stands for impervious surface area, with NOx in the top two plots and ozone in the bottom two plots. Again, these are split with edge values in black and interior values in gray. You can see that both concentrations increase with urbanization, while edge concentrations indicated by the blue arrows are significantly higher than interior concentrations in the case of both NOx and ozone. We can see, looking at the blue boxes here, that this pattern is especially prominent in urban forests, where our NOx concentrations reach higher than 6 parts per billion. Overall, we did find that urbanization increases nitrogen deposition and edge tree exposure. Spring enhancement was found in throughfall, which implies canopy processes or fertilizer input, while the higher bulk deposition implies a fertilizer contribution. This is particularly interesting, again, because the county in which Harvard Forest is located is the county with both the most farmland per acre and the most farms in Massachusetts. We also found significant urbanization effects in throughfall nitrate, which are likely due to fossil fuel combustion in urban areas, as studies show Boston vehicular emissions align with atmospheric nitrogen deposition. In terms of NOx and ozone, we found elevated concentrations of both at urban forest edges, while concentrations at the edge and interior are similar in rural forests. The concentrations do decrease throughout the growing season, but the seasonality itself doesn't match the ozone measurements provided by Massachusetts DEP. This could imply that edges or urbanization are exacerbating ozone concentrations. Our results have implications for nitrogen cycling in urban forests. They account for urbanization and fragmentation impacts, which are both ecological concerns for nitrogen cycling. Our results also explain components of nitrogen fluxes at urban forest edges compared to interiors and rural areas. They also show insight into the sources driving the nitrogen fluxes as a combination of fertilizer canopy processes and fossil fuel inputs. Finally, our results display the importance of edge effects on ambient Nox and ozone concentrations, as they have potential for increased damage to urban edge trees and in turn decreased net carbon sequestration. Thank you very much to all of my funding organizations and to the people who have helped contribute to field and lab work, and to all of you for joining my talk today. And I'd be happy to take questions at this time.
Wonderful. Thank you, Jenna. And I'll clap. You could stop sharing if you like so you can see folks. We already have a question from Doug Burns, who asks, have you learned enough to be able to map the deposition of these pollutants onto the larger landscape at a scale such as statewide?
I am fixing my screen. Yes. In short, yes, I think that we have. I would hesitate to map it to the statewide scale just because we only have our gradient from central Boston to central Massachusetts. We haven't mapped it all the way to western Massachusetts yet. So I would hesitate to extrapolate, but yes, in general, I do think that we could use that to map at least our area so far.
Wonderful. Thanks, Jenna. Jeff Herrick asks, maybe you could look at how close farms are to Harvard Forest. Petersham is on the edge of the county, and that's the largest county in the state.
Yes, so I did reach out to their the state's agricultural expert. Yeah, I forget what his actual title was, but I did reach out to the state's agricultural expert, and I am waiting on data from him. It's sad that I couldn't get it for this talk, but I will hopefully have some answers soon.
Wonderful. Thanks, Jenna. Sarah Nelson says, great talk. I may have missed it, but are you collecting through fall and winter as snow? It can have much higher nitrogen concentrations.
We are not collecting through fall in the winter, but we are conducting another study next year on deposition, and we will be doing those throughout an entire year. So we will have some winter data for you soon.
Wonderful. Any other questions, comments for Jenna? So Jenna, I'll just ask a quick question. I'm curious, many past studies have shown very large edge effects for through fall, but we did not find that in our study. Do you want to posit on that at all?
Sure. I think, well, we do see edge effects in our ozone and Nox more so than our nitrogen through fall deposition. It's definitely, I definitely think that the urbanization gradient is affecting that greatly. But based on our influence, what's influencing our data, I do think that it's locational based. So if we're looking at more farmland, more fertilizer, that might have more contributions. But then when we move into urban areas, then we're looking at more fossil fuel contribution, and those two could balance each other out essentially. So I do think that we could use the other data that we've collected at the other parts of our transect, such as temperature, air temperature, soil moisture, soil respiration, and try to use those to answer some of these edge effect questions.
Great. Greg Weatherby asks, could these results be incorporated into an algorithm to influence deposition maps for better representation of urban deposition? For example, adjust the NADP nitrogen deposition based on road density.
Yeah, so I definitely think that could be useful. in terms of looking at the NADP values in Boston, they do find higher levels. They do have higher levels of nitrate deposition and ammonium, which aligns with our results. I haven't conducted the actual unit conversions yet to determine if they're on the similar magnitude as our bulk deposition. But as of right now, the deposition on top of our building in Boston do align with what we're seeing so far. So I do think that they could be used for that sort of calculation, yes.
Wonderful. Thank you, Jenna, so much for an excellent talk. Okay, we're going to move on to our next talk. So our next talk is by Francesca Borelli, and we're going to hear about bioaerosol occurrence in working places. You can go ahead and share your screen. Next, we're going to hear from Lillian Namey, who's going to talk to us about air quality in Rocky Mountain National Park during the 2020 COVID-19 shutdown. Good morning, Lily. You can go ahead and share your slides.
Awesome. Good morning, everyone. Thank you for coming. There we go. So just before we get started, if you're looking at this on Zoom, just wanted to let you know that if you pin the speaker view to the upper left-hand corner, it won't cover any of the plots. So today I'm going to be talking to you about air quality in Rocky Mountain National Park, as already stated, during the 2020 COVID-19 shutdown. And I'd like to say a big thank you to the National Park Service, Colorado State University, and all of my co-authors on this project. So as I'm sure you all know, COVID-19 has impacted our lives in a pretty profound way over the last months. These are just a few of the headlines from that time, and many have been curious as to how the shutdown and sort of the slowing down of driving, et cetera, could impact pollution and air quality. So to talk a little bit more specifically in Colorado, so this is a map of Colorado, and we're going to be talking about the shutdown period as this April to May time period. And the reason for that is that the stay-at-home order released by the Colorado government ended on May 31st, and we weren't able to start data collection until April 25th. So for this, that's also the time period that I'm talking about. So a pretty significant way that the COVID-19 shutdown has impacted Colorado is in this traffic decrease. So for that time period along I-25, the main highway for us out here, there's about a 30% reduction in total traffic. And then that upper arrow is in Estes Park, which is the city right outside of Rocky Mountain National Park that I'm going to be talking about today. And they had a 40% decrease in traffic throughout those 2 months. So you might also think that with everything slowing down, agricultural emissions would also be decreased, but it seems like from talking to members of the ag community that it's actually stayed about the same. So for this talk, we're going to be talking about air quality data from 2 different sites. The first is in downtown Denver at 2105 Broadway, and it's operated by the state of Colorado. And then the second is the Longs Peak Air Quality Monitoring Station, which is at the base of Longs Peak, a 14,000 footer in Rocky Mountain National Park. And it's operated by the National Park Service and is where all the data that we as CSU collected was taken. So to start, we're going to look at the air quality in Denver as kind of motivations for why we're looking at Rocky Mountain National Park as well. So this data is just for April 25th to May 31st, comparing these concentrations across years. So the dotted line in the middle is the mean. The box of each data shows the upper and lower quartiles. The whiskers represent the range, assuming the data matches a normal distribution, and the dots are outliers. So starting with that plot on the right, we're looking at PM 2.5 over these about 2 months. And it really doesn't seem like, looking at the mean values, that there's much of a trend in recent years. The mean is kind of bouncing up and down as the years go on. However, if we look at the NO2 plot on the left, the mean values do seem to be downtrending over recent years, and there's a pretty significant drop between 2019 and this year, which is interesting to see. So Rocky Mountain's pretty far away from Denver. Why do we care about the air quality in Denver when we're really looking at Rocky Mountain? And that's because of this mountain plains circulation that's characteristic of the region. So I have a diagram of that on the left. And basically the Colorado Plains source regions have a large impact on Rocky Mountain because of this upslope flow. So as wind comes off the plains, it brings high concentration air masses up into the park. So that black triangle is the approximate location of the Longs Peak Air Quality Monitoring Station, to put it into context. And the plot on the right is a windrows of wind data from this specific site over the shutdown period. So what I'd like you to note here is that it's pretty much separated into two modes, which are both characteristic for this region. There's a northwest mode and a southeast mode, and that southeast slice is what we're going to talk about for this specific site as the upslope flow, or flow coming up off of the Colorado Plains. Good to note here that those modes would be a little bit different depending on where specifically it was taken. And this is from specifically the same spot that we took our other data. So to key back into this map, now that we have a little more context, you can see that under Rocky Mountain, there's this big stretch of mountains, and then the plains are sort of due east. And that's why we care so much about these source regions in the plains, is because they can bring high concentration air masses up into Rocky Mountain National Park. So to look at this air quality in Rocky Mountain, we used URG denudor filter pack trains to measure particle and gas species. The frequency of this sampling began at daily on April 25th, and then was switched to twice weekly on June 8th. We also collected precipitation samples using the precip sampler on the left. Precip samples began with bucket switches 3 times a week, and then switched to twice weekly on June 8th. So with this data, we're paying special attention to reactive nitrogen species because of their contribution to excess nitrogen deposition and its historical impacts on the Rocky Mountain ecosystems. So both of these types of data collection are going to be compared to previous years of data to explore if the Rocky Mountain air quality has significantly changed during the COVID-19 shutdown. So to start off, just looking at a timeline of the URG denudor filter pack data, I think it's interesting to see here that you can pretty visually identify the sampling frequency change on June 8th. And especially interesting to see how some of the variability is lost when you change that sampling frequency. So if you look at the nitric acid and nitrate plot in the middle, I think it's interesting to note that the daily samples seem to capture the variability in particle gas partitioning. I'm looking like specifically at May 15th, where you can see the fractional contribution really change, but the longer timescales samples appear to have a more constant fractional contribution. So we're just losing some of that variability. So while it's interesting to look at this longer timeline, the rest of this talk, we're just going to dive deeper into the shutdown period, which again is April 25th to May 31st. So thinking about that windrows and how upslope flow brings these high concentration air masses, we wanted to look at the amount of daily upslope flow and see if it trended with increasing species concentration. So to do this, we downloaded hourly meteorological data from the National Park Service, which was taken at the Longs Peak site. And then upslope flow was defined as from the southeast quadrant, which, if you can remember back to the windrows, was one of those modes we were talking about. And then percent upslow is defined pretty simply as just the percentage of hours during the day that the concentration sample was taken for which it was experiencing upslope flow. And when we dive into these plots a little bit, the y-axis for all of them is the percent upslope flow for the given day, and then the x-axis is the concentration of those various species. And the points do seem pretty scattered. However, it does, at least visually, look like there's a little bit of a trend, a small correlation between this increase in daily upslope flow and an increase in concentration. Also important to note for these plots that the open circles are days that had precipitation and the closed circles are days without precipitation. So to investigate this a little further, we did the same sort of analysis, but summed the particle and gas species to see if that would lead to a clearer trend. And it actually does appear that when you consider them both, the particle and the gas from URG species, that there's a clearer trend between upslope flow and species concentration. And this supports previous data indicating transport from these downwind plane sources. It is also important to note here that this is a pretty simplistic analysis of transport from the plains region. There are folks doing much more complicated work, and we are planning to use some backtracer analysis to look at this a little bit more deeply moving forward. But for now, it at least is an interesting starting off point. So then to look at the yearly comparison of these particle and gas concentrations, again, still just looking at April 25th to May 31st. In these plots, 2019 is excluded because the URG data was taken at a different time frequency than other years, which just makes it a little bit tricky to analyze in a plot like this. When we look at the mean values, which are again represented by those dotted lines, it's interesting to see that the means are a little bit higher in some cases, a little bit lower in others. Pretty much across the board, though, they're exceptionally similar to previous years, perhaps with the exception of SO2 in that upper right-hand corner, where the mean is lower than previous years. However, that species is at a pretty low concentration in Rocky Mountain, so it's hard to really say. So again, we wanted to see if summing the particle and gas species could remove some of this noise. And it is interesting to see that when we look at the sum of those means, there actually is a little bit of a decrease from previous years, specifically 2018. However, it looks pretty similar to 2016 and 2017. And due to the variability in the concentration values, it's hard to say. So the other big thing that we wanted to look at was this nitrogen wet deposition through the precip sampling. So we're looking at just a species contribution over 2020 to nitrogen wet deposition in this region, with the shutdown period having a red box around it. And as we normally see for this region, the wet dep is dominated by ammonium, has a significant contribution from nitrate, and a really variable amount of organic nitrogen. We especially care about this, again, because there's been this historical record of significant ecological impacts from an increase in nitrogen deposition in Rocky Mountain National Park, which, because of its high elevation, developed in a nutrient-deprived system. So to further analyze this, we compared nitrogen deposition to previous years. So that plot on the left is looking at the cumulative nitrogen deposition from April 25th to May 31st for each of the last 5 years. And at first, it looks really exciting because the 2020 cumulative wet deposition is a lot lower than those previous years. However, when we normalize it by the millimeters of precipitation over the same amount of time, which is represented by the red dot on that left plot, we actually find that the normalized wet deposition by precipitation is very similar to previous years. It is interesting to note that the 2017 normalized value is significantly lower. So I would be interested to dive a little deeper into that and see if across the year that was the case. At least for this year, the total wet deposition normalized by precip was really similar to previous years. So for some key takeaways from this talk, first talking about that Denver data, I think it's interesting to see here that it's more straightforward to see trends in species like NO2, whereas when we start looking at species that develop over longer time and spatial distribution, the trending is just a little bit harder to see and comprehend. And then in terms of our URG, the mean values of particle and gas species are similar to previous years, and it's going to require some much more complicated statistical analysis to really analyze and understand if they're significantly different from previous years. And my last thing is that when we look at that cumulative nitrogen deposition, especially normalized by the precipitation amount, it's comparable to previous years during the shutdown period, and will be interesting to see moving forward if that is true after the shutdown period. Any questions?
Wonderful. Thank you, Lily, for an excellent talk. We already have a couple questions. So Vid
Awesome.
Grande, yeah. So Vid Grande asked, how much of the loss of variability with increased sample time is related to chemical changes during sampling?
That is a great question. I am truly not sure. I would love to connect with you and talk about it more at some point. My general understanding is that most of it is simply due to the way that it averages out. So if I think I can flip back. Yeah. So if we look at this, like if we key in on that May 15th and that nitric nitrate plot again, I think that the change in sampling frequency, what it's really doing here, like looking May 15th to May 17th, is just averaging out that particle gas distribution, which, because it varies sort of day to day, you end up with this much more smoothed graph after June 8th when it's that 3-day frequency.
Great. Jim Renfro asks, did you normalize the wet deposition by ammonium and nitrate separately?
No, for the purposes of this analysis, it was just by the total nitrogen wet deposition, but it definitely would be interesting to dive a little deeper into the species contribution normalization.
Great. Doug Burns asks, would you say that your data suggest that much of the particulate matter at Rocky Mountain National Park must originate from non-transportation sources?
I don't think I would say that. I think it'll be interesting once we can do that back trajectory analysis to dive a little bit deeper into those source regions. I think where it stands now, there isn't enough from this year to say that it would change the previous data supported idea that the transport's coming from the Colorado plains. But I do think it'll be interesting to look more in depth at and see what's going on this year more specifically.
Great. Greg Weatherby follows up and says, echoing Doug Burns, do these results suggest that the sources to Rocky Mountain National Park are largely agricultural versus urban?
That is also a great question. I think yes. And I think my understanding from previous data we've supported as well, data we've done has supported, sorry about that, that these ammonia emissions from agriculture that are due east of the national park has a huge impact on the national park, especially because it's unregulated emission and we don't really have a good idea for how much people are producing and at what time.
Great. We have time for more questions if people have any. In the meantime, I'll ask one. I'm curious, it seems like many people have taken advantage of the COVID period to look at what happens when human activities go down. I'm curious, if you had an unlimited budget, I handed you $1 billion, what else would you have measured in Colorado, or I'll give you the whole United States or the whole world? What would you measure if you could measure anything related to air quality and deposition?
Oh, that is a fabulous question.
You don't have to have $1 billion. I can give you like 5 million if you want to start smaller. I'm just curious, what else would you have added if you could have added anything?
Yeah, I think if you had an unlimited budget and folks who were capable of doing this, I think it'd be exceptionally interesting to look at it from a satellite perspective and see, or if you had an unlimited budget, just set up a lot of sites on the ground, but to look at spatially like across the United States, if you could see when different states were ending and beginning their shutdown periods, based on like a super wide network of data collection, I think would be really interesting.
That would be. Well, thank you so much for an excellent talk. Really great. Thank you, Lily.
Thank you.
Wonderful. Okay, so we now have our last talk of the session. Timothy Chirac is going to talk to us about CastNet ozone responses to COVID-19 related impacts.
Okay, thank you. All right, so I'm Tim Chirac with the CastNet program out of EPA's Office of Atmospheric Programs, and we very interested in the impacts from COVID-19 related responses. Can we see a signal in our CastNet ozone record? I want to shout out to our co-authors here for this talk. So, brief outline, talk about CastNet, what CastNet is, what's measuring, objectives and methods in the study, discuss the results, and wrap it up with a summary and next steps. So CastNet, similar to NADP, long-term monitoring network located in rural locations. We have 97 monitoring sites. 86 of these sites have ozone analyzers. Long-term records going back 30 plus years. Generally, we're co-located with NADP, almost always. Our network design is to be away from large emission sources, to see long-term trends. What does the general natural environment see? Great national coverage, although fewer sites in the West, and we're regionally representative. Our analyzers are atop of 10-meter towers, and we're trying to provide a baseline or background ozone signal. So this is a tall order, but we're trying to identify and quantify the changes in our CastNet ozone record as a result of impacts, stay-at-home related orders and other impacts we see attributed to COVID-19. So we're primarily comparing 2020 versus the last 5 years, the 2015 to 2019 ozone record. Caveats, and there are many, and they're big. Much of these data are preliminary and have not been fully quality assured. And also, ozone concentrations fluctuate from year to year for non-COVID-19 related impacts due to meteorological and wildfire impacts, which have negative and positive impacts to ozone formation. Ozone levels, as a general rule, have been declining over time due to air regulations. Lastly, stay-at-home orders vary significantly in timing, duration, and implementation. And we'll show that. So our methods, we're primarily looking at the 90th percentile 1 hour ozone and temperature values in 2020 and comparing those with previous 5 years from 2015 to 2019. We examine stay-at-home orders to look for temporal changes. And then we look at some Department of Transportation vehicle miles traveled maps and NOAA climate maps for spatial patterns and see how our CastNet data respond in those kind of different time periods and different spatial regions. So here's our data. Basically, here's 2020. And so this is a mess, but let me walk you through it. Up top is the, great, it says the internet connection is unstable. The blue line is basically our 90th percentile 1 hour ozone value over the last 5 years. So this specific week, this week saw 55 ppb of ozone. Like I said, the 90th percentile in the last 5 years, but in 2020, we see 52.4 ppb for that specific week. Now, if we scroll down, with our eyes and look at the baby blue, we see, well, the difference between those two values is negative 2.6 ppb. So we're 2.6 ppb below average, for that specific year. It's by week of year, which represents a 5% below average. And then the bottom plot in yellow shows that we are 1.4 degrees Celsius above average. So we're warmer temperatures, yet we're seeing below average ozone concentrations. So let's look at 4 different time periods here to see kind of what kind of changes do we see. Now, in period 1, this is the average stay-at-home period, spanning March 23rd through May 17th. States varied wildly, and we'll show that in the next slide or in a future slide. But in general, across the country, for the 43 states that shut down, that had stay-at-home orders, this was the time frame that we looked. And we see, yes, pretty significant reductions in ozone concentrations, 4.5 ppb below their 5-year average. But it was a very cold spring, and average air temperatures were 1.7 degrees Celsius below average. Looking at the next period, what happened? So that was during the stay-at-home period, the average stay-at-home period. What happened since the stay-at-home period orders were issued till today, or October 11th, I should say. Similar ozone, ozone reductions are down. They're not down as much, but they're still down a little. Despite of, we're still including that time period of that cold spring. So we're about average, but slightly below average. We had above average temperature summer. Now let's talk about summer, third period. The months of June, July, August, we see, slight reduction in ozone concentrations, despite slightly above average temperatures this summer compared to the previous 5 years. And lastly, kind of what happened subsequent after the average stay-at-home orders were lifted. Well, we see, till today, we see slightly below average ozone values, and slightly above average, or basically average air temperatures. Lastly, I thought this was pretty interesting. In the last 5 weeks of our data record here, we see that ozone and temperature are kind of tracking in the same direction. What I mean by that is on the weeks that we see above average air temperatures, we see above average ozone values, and similarly, when we see below average air temperatures, we see below average ozone concentrations, which is what we would expect. But those aren't the patterns we saw typically during the stay-at-home orders or previous time periods. So let's look at our cumulative ozone exceedances, in 2020 versus the last 5 years. Let's look at the 2015 ozone max. We see up until approximately, August or so, we were tracking to have the second lowest number of ozone exceedances across these 75 CastNet sites. We're only looking at 75 CastNet sites because those have a sufficient data record. And then we had, I guess California and the Intermountain West experienced one of the largest the largest wildfire season on record, or one of the largest wildfire seasons on record. And we experienced 32 ozone exceedances over the span of 3 days, spanning from California to Wyoming. That certainly bumped up the number of ozone exceedances, but we're still, third fewest number of ozone exceedances. If we look at the 6-year data record. If we exclude California and the Intermountain West states, we see there were only 6 ozone exceedances. And this would be the fewest on record. Now we know that ozone is very sensitive to air temperature and precip. So we'll look at air temperature. So let's look at cumulative days above 90 degrees or 32.2 degrees Celsius. We see ozone, especially in the summer, was 2020 appeared to be a particularly ozone conducive year for high ozone conditions. If this were any other year, it's a pretty warm year this summer, and I think it would have been. But we also had a record hurricane season this year, and that seemed to perhaps curtail the number of days above 90. And so we were on track to be a very warm year, but then, that kind of stopped right around Labor Day. So these are our temporal patterns here that we see in the data record. Now let's look at the stay-at-home duration. And all I can say is that it varied substantially across the country. We see patterns where we see in the Northeast US, longest stay-at-home duration, and they started earlier and they ended later. Quite a lot of variety. The longest stay-at-home duration state was in New Jersey at 75 days. The shortest was Mississippi at 23 days. So the Northeast, as well as the Western Pacific states and New Mexico, had the longest stay-at-home duration. So this kind of gives us an idea of spatial patterns. Midwest, some states, 7 states, primarily in the Midwest, did not have stay-at-home orders or restrictions. Now, if we compare stay-at-home duration for each respective state and compare the amount of reductions, ozone concentrations seen in those states compared to 2020 versus the last 5 years, we see there's a slight trend. States that stayed home or had longer stay-at-home orders trended or seemed to have larger reductions in their ozone concentrations. This kind of made sense, but we filtered the data to remove the weeks that were outside of plus or minus 2 degrees Celsius. But in general, there's a slight pattern. So, stay-at-home orders, we've all stayed home. What's driving these patterns, or what other supporting evidence would we look at? Well, this is Department of Transportation's average vehicle miles traveled. So this is comparing April of 2020 with April of 2019, and we see across the country. In general, vehicle miles traveled was down 40%, pretty consistently across the U.S. Although 46% or 47% in the Northeast. So April of 2020 saw the fewest miles traveled, going back to 1995. Why are we looking at this? Because, the 2017 EPA's NEI, National Emissions Inventory, shows us that the on-road mobile emissions sector is the largest sector of NOx emissions at 35% of anthropogenic. So we're looking at patterns here, and what do we see in April, when kind of the peak of the stay-at-home orders nationwide? We see Northeast states in general, pretty, as a solid block, saw the largest reductions in vehicle miles traveled, as well as, we saw this in the previous map, the Pacific states. But it varied. And now if we compare that period with summer, we see it's not back to normal, but Northeast, had, well, this makes sense. They had the longer stay-home duration, but they also they had larger reductions in vehicle miles traveled. Now, this is not to imply that these are the percent reductions of NOx emissions. We certainly can't say that. We don't know anything about emissions. We don't have any emissions data, but using vehicle miles traveled as some some form of information to tell us kind of where are their patterns, spatial patterns. So another form of information to look at, comparing, knowing that ozone data are very sensitive to meteorological inputs. Looking at Northeast US, we see in the, this is 2020 summer, comparing those maximum temperatures with the long-term climatological record at NOAA. We see the Northeast US seeing, much above average air temperatures, as well as the west, southwest. Reflects, whereas you also see below average air temperatures in much of the Southeast. You look at the mirror image of this map in precip, pretty good surrogate. Increased precip will reduce ozone concentrations as they are. So we see above average precip across much of the Southeast, including the north central or northern Midwest parts of the country, as well as Idaho. So these are we're looking at the general consensus of what other factors may explain reduced ozone concentrations despite stay-at-home orders. So when we put all together are these different regions and these different time periods and perform paired t-tests, we see that we do seem to see some significant differences in ozone in the data record of 2.5 to 4.5%. But are these really significant? Are these really attributed to COVID-19 related stay-at-home orders? Well, take into effect that 2020 experienced a record hurricane season and a record wildfire season. That those factors appear to just our best estimate here appear to be a likely larger contributor to reductions or changes in the data record than, say, stay-at-home orders. So, and kind of taking into account the vehicle miles traveled in different portions of the country, it appears that northeastern U.S. had the largest change in vehicle miles traveled, and probably had less impact from the record hurricane season and record wildfire season. So this seems to be the only part of the country that, it's plausible that we may have seen a signal from the COVID, stay-at-home orders. This state also had the longest duration. So, this is the best guess we can provide based on the information we have. We don't have CO, we don't have PM 2.5, we don't have, most of our sites don't have on-site meteorology. We don't have LIDAR or ceilometers to, give a great sense of, information to provide, source attribution studies. But based on the ozone data record and our temperature record, this kind of makes sense. So summary, stay-at-home orders occurred during a cooler than average spring, greatly knowing that ozone is very sensitive to meteorological inputs, greatly challenged our capacity to see whether or not those stay-at-home impacts really, reduce the ozone concentrations. Cast-net ozone exceedances were the third lowest, over the last 6 years. But, especially, and we're certainly the lowest if you exclude the wildfire impact states. Now, states that stay at home, had the longer stay at home orders generally had larger ozone reductions based on what we can see. And it's plausible that longer stay at home orders and the resulting reduction in vehicle miles traveled, appeared to align with ozone reductions in the Northeast, despite above average temperatures. And that's kind of it. Next steps, we're looking at ozone formation rates using, the rate of increase in ozone diurnal profiles to kind of give act as a surrogate for NOx emissions. But, we're still very, very early on that. We do see some trends at some of our sites, in the later summer months, if we compare, say, 2020 versus a few years earlier. But very early to tell, and a lot more work to do. But and that's it. Any questions?
Yeah, thank you, Timothy, so much for a great talk. We have a lot of questions in the chat. So the first one,
okay,
that's great. The first one comes from Donna, who says 2020 is an NEI year, but also has very different emission patterns. How will this impact building the 2020 NEI and the use of that inventory to develop emissions for non-inventory years?
2020 has been a very funny year. Well, in terms of the inventory, I really know very little about the actual inventory number, but yeah, based on some of the satellite imagery, it is suggestive that 20 or 30% reductions in mobile emissions seems plausible, but boy, I mean, that doesn't translate into 40% reduced ozone concentrations, that's for sure. So, but it does seem like there would be a significant impact to the NEI when it does come out in, I think, late 2022 or early 2023.
Great, thank
Next
you.
question.
Doug Burns asks, analyses in some countries and cities across the globe have shown big drops in NOx, but much less change in ozone, which investigators have attributed to an increasing role of the hydrocarbon precursor pathway. Can you relate your ozone findings to the predominance of the NOx versus hydrocarbon formation pathways?
Well, I think one of the, I've seen a little bit in the primary literature that's saying that actually some cities are seeing, increased ozone concentrations, but we have to, some of the things we have to take into account are that, Castnet's a very unique record, and we're primarily NOx limited. We're in rural locations, whereas, in terms of regulatory ozone monitors, most of those are located in VOC limited environments, in urban environments. And so if you reduce NOx emissions, ozone values sometimes go up in those environments, whereas Castnet oftentimes sees the other way around.
Okay, Stuart Weiss says, looks like some modeling studies would elucidate some of the patterns. What would you suggest?
Oh, which modeling patterns to? Oh, I'm not quite sure on that one.
Okay.
But yes, yeah, we certainly do need to look at modeling. We've been looking at some satellite imagery, but yeah, it is. There are a lot of things to untangle, I should say.
Definitely. Amanda Cole says, are there long-term trends in the 90th percentile ozone that may contribute to the differences between 2020 and earlier years?
Certainly. Yeah, it really depends on the meteorology, how ozone conducive a year was. But, I think 2018 was a particularly ozone conducive year. And so coming back down off that high, I think 2016 was ozone conducive year, but 2015, I think, and 2017 were particularly low years. So it really, when you compare emissions, we know we're trending downwards, and the record itself is likely going down. But it did seem to make sense to compare this 2020 versus the last 5-year record to kind of normalize out those meteorological impacts.
Greg Weatherby asks, so if taking 40% of the vehicles off of roads for 2 months only reduced ozone by 4%, what can be done to reduce ozone?
Oh, that's a do it all year, I guess. No, that's a very challenging question. Yeah, I think I'm not quite sure. You know, it was a very, I think, well, what I see is, yes, that was true. We reduced traffic emissions we reduced vehicle miles traveled by 40% in April, but that was not a particularly ozone conducive year. I mean, that was not particularly ozone conducive season. So that impact, would have a very moderated impact to the ozone record. But if you were to shift, if we were to redo this experiment and shift it to July and August, then I'd likely see a much larger reduction in ozone concentrations.
Great. All right, we're running out of time, but we'll do just 2 more quick questions. Rodolfo Sosa says, very nice talk. What could have been the influence of wildfires on ozone concentrations?
Oh, great question. One of wildfire impacts, from what we see, is that it can contribute, depending on the intensity of the fire burn of the wildfire, it can generate a great deal more NOx and contribute to higher ozone formation, or it can smolder if it's cooler and then just block out solar radiation and lead to lower ozone concentrations. So it's not one way or the other. It can do either or, basically depending on smoldering versus really high hot temperature wildfires.
Okay, one more quick question. Did all road traffic go down by 40% or was it variable by sector?
I'm sorry, once more, please.
Sure. Did all road traffic go down by 40% or was it variable by sector?
Based on some of the limited information I have, it did seem like passenger vehicles, came down quite a bit. But from what I understand, the heavy duty trucking and fleet vehicles, based on, I think, INRAC's dashboard data. So it suggests like heavy duty trucking, which are much higher NOx emitters per unit. Those remained on the road, shipping all our Amazon packages, just as we expect. But in terms of vehicle miles traveled by passenger cars, which are much lower NOx emitters per unit, we did as we told them, we're basically remain inside. So
wonderful. Well,
it was a mixed bag.
Yeah. Well, Timothy, thank you very much for a great talk. And I'd like to thank all of our speakers for this session for doing an outstanding job. Thank you very much. And I'll hand it back to Greg and David.
Great session, Pam. Great session, all the speakers. Really mind-blowing talks, I thought. I mean, a lot of different topics on effects from people, right? So, I mean, that's kind of what this session was about. And I want to invite people to become more involved with NADP by tuning into the City Dep Committee. We're especially interested in effects in urban environments and trying to expand NADP into urban centers. So if you have interest in that, please email me and we'll get you connected, or you can email Pam, because Pam's a staunch supporter of City Dep. So again, thank you so much for this session.